Good morning, everyone. My name is Ian Jiang, the author of this paper. Dr. Zizhi Jing can't be with us today due to some unexpected situations. So I will present this paper on behalf of him. This paper is about EMI attack against LiDAR, named PhantomLiDAR. LiDAR is a sensor widely used in self-driving car and robotics for 3D perception. Correct sensing of LiDAR is the foundation for system safety. Therefore, LiDAR security is important, and the research goal of this work is to make the LiDAR more reliable. So, how does LiDAR work? LiDAR perceives the environment by generating point cloud through laser ranging and laser scanning. During laser ranging, 1 point can be acquired according to the time of flight principle. LiDAR emits a laser pulse at each direction, which hits an object and reflects back as an echo. The distance of that point can be calculated based on the propagation time. During laser scanning, LiDAR can change the laser firing direction and scan the surrounding environment to generate point cloud. Compared to other works, such as a camera or microphone, LiDAR is a relatively complex system. In order to analyze the vulnerability of LiDAR more systematically, we first need to understand the foundation modules of LiDAR. This is a typical commercial LiDAR system, and we will start by disassembling it for further analysis. A typical LiDAR system consists of 4 key functional modules: an emitter, a receiver, and a beam steering module to adjust the laser emission direction, and the main board to handle signal processing. One critical question is how safe LiDAR is. Numerous studies indicate that LiDAR can be compromised by laser, and a recent work indicates that LiDAR can be compromised by EMI. Previous works all considered the receiver as a attack surface, focusing on manipulating laser ranging to attack LiDAR. The vulnerability of other modules within the LiDAR system remain unexpected. To fill up the research gap, we proposed the PhantomLiDAR. By injecting different EMI signals into different attack surfaces, we can achieve 4 types of attack effects, including point interference, points removal, LiDAR power-off, and points injection. The attack surfaces of PhantomLiDAR includes the laser receiving analog circuit in the receiver, monitoring sensors on mainboard, and the optical encoder in beam steering module. PhantomLiDAR is based on 2 attack principles. The first is direct attack. By interfering with the analog signal in the receiving module, it directly disrupts the LiDAR's ranging process, consequently corrupting the point cloud. The second is indirect attack. First, the attack induces error in the auxiliary circuit. Thus, by exploiting LiDAR's force detection and diagnostic mechanism, these errors can indirectly trigger the services issues such as point removal of LiDAR power-off. For example, abnormal temperature may induce point removal. Abnormal rotation speed may induce LiDAR power-off. Next, let's dive into details of 4 attack effects. Let's begin with point interference. As shown in the slides, the attack effect involves introducing errors in LiDAR ranging, thereby distorting the point cloud. The principle is direct attack. When we inject a sinusoid EMI signal into the receiver, it mixes with the benign echo signal. This causes minor variations in the peak time of the echo signal, which then interfering the laser ranging process. Next, let's talk about point removal. The attack effect here is that points either move far away or disappear completely, as if they have been removed. We discovered the 2 principles of point removal. The first is direct attack. The attack surface is still the analog circuit in the receiver. The difference is, in this attack, we use high-amplitude sinusoid EMI. This will saturate the receiving circuit, making the echo laser pulse undetectable. The second attack principle of points removal is indirect attack. In this way, the attack surface is monitoring sensors, such as the temperature sensor. This principle is compromising the temperature sensor, leading the FDD mechanism of LiDAR to treat some or all points as invalid, as shown in the figure. When EMI is off, the temperature is stable around 14 Celsius. When EMI is on, the temperature fluctuates dramatically. The LiDAR Power-Off attack can cause its LiDAR system to shut down and stop working. The attack principle is indirect attack. The process is to compromise optical encoder in beam steering module to induce wrong rotation speed, inducing the FDD mechanism to cut off LiDAR's power to protect itself. As shown in the figure, when attack is on, when we can see the rotational speed of the LiDAR dropping significantly, ultimately causing the system to power off. Finally, let's have a look at point injection. As the name tells, we can inject controllable points into LiDAR with EMI. This is direct attack, and the attack surface is still the analog circuit in the receiver. Importantly, in this attack, we designed the attack signal using amplitude modulation. Specifically, the carrier signal is a sinusoid wave. The baseband signal consists of fine-grained pulses. The amplitude modulated sine wave can forge echo signal to achieve point injection. If you are interested in the detailed design of this attack, please refer to our paper for more information. We conducted many real-world experiments to evaluate PhantomLiDAR. For time reason, we quickly go through of them. The figure shows that the typical experimental setup. The attack device includes a signal generator, power amplifier, and an antenna. First, we tested 5 commercial LiDAR modules. By fuzzing these systems with EMI signals, we discovered that different LiDARs have distinct vulnerability, offering insights for future design. For points interference, we have measured interference intensity using distance errors. Our attacks can induce over 10 centimeters error. Then we explored the impact of the attack on 3D object detection models. We find that sensor fusion can mitigate point interference effectively. This observation may provide guidance for defense. For points removal, firstly, we find the attack has long attack distance and low location requirements compared to other EM-based attack. Additionally, we evaluated the aiming requirements. The results show very low aiming requirement when compared to laser-based attack. For points injection, we succeeded to inject spoofing point cloud with different patterns, such as wall or pedestrian. At last, we conducted real-world experiments with moving vehicle. Our attack goal is to compromise the victim's LiDAR and make the LiDAR-based 3D object detection model unstable, unable to detect the target object. Please visit our website for experiments videos. We summarize our contributions as new attack surfaces, new attack effects, and strong attack capability. Thanks for listening. And if you have any questions, you can contact the author, Zhijing.